Salutations from the stars. Professor Copperstein here with your lesson on Newton's laws, all three of them. So, let's begin. The first law being the law of inertia. For every object at rest shall stay at rest unless acted upon by an equal and opposite outside force. Likewise, an object in motion stays in motion unless acted upon by an equal and opposite outside force. Yes. So what it's talking about is the fact that an object, whether it is moving or staying still, will stay like that unless something pushes it. Here, let me get an object, my cheese. It's resting on my hand. Now if I push it like this, it's now moving. If I stop, it's not moving anymore. The force of friction stops, it's moving. If there was no force of friction between the cheese and my hand, then it would have just kept on sliding after I stopped pushing it. It would have just right off my hand. But that's not the case. Friction wins. So, let's have another example. Another example involving my watch. Now, I am spinning my watch in a circular path. Tell me, is my watch accelerating? It's not moving faster. It's not slowing down. So at this point, you might want to say no, it's not accelerating. But that would be incorrect. Something you must understand about vectors. Alright, let's look at this. I'll be right back. Alright, here is my lovely drawn circle. Here is my hand in the center. And here's my watch. And that's the chain holding my watch. Alright. Right now, due to gravity and the force applied by my hand on the chain and onto the watch, this is the direction that my watch is going at the moment. This is what is known as the tangent. However, as I am constantly twitching my wrist at a circular path, it causes my watch to change direction. So now it's on a circular path, finding new tangents along this circular path, going forth and forth and forth and forth, circular, 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 constantly changing direction due to a constant force that I am applying with my hand. So there. Because of this, it is safe to say that in fact my watch is accelerating. Alright, so, of course, it doesn't always have to matter the speed of an object. Just simply changing direction counts as an acceleration because forces are applied to it. And this is what is known as the difference between vectors and scalars. Velocity is a vector because it is magnitude and direction. Speed is just magnitude of speed, and thus it is a scalar. Alright, so moving on to the second law, we have force, mass, and acceleration. The law of force, mass, and acceleration states that force has an inverse relationship with the time in which the acceleration occurred, and a direct relationship with the acceleration itself. And thus we get this equation. Force equals mass times acceleration. We can see the inverse relationship with time through dimensional analysis. Sorry about that. That is the dimension of mass, and acceleration is distance times time negative squared. It's distance divided by time squared. And so you can see how this has an inverse relationship between time and force. If you were to graph this in a force versus time graph, and make f as a function of t, the graph will look like this. This is what results in the inverse relationship that you see with time. With the acceleration itself, of course, that's the direct rule. So yeah, that is the direct relationship that it has. So if you'll notice that if at any moment, so with this equation, you'll notice that bigger masses result in less acceleration if you apply the same force. Because if you divide the force by the mass, you realize bigger m is a smaller a, and thus. So if you want to make the acceleration the same with the bigger mass, you'll have to make a bigger force in order to offset that deficit. So, and now for the third law, the action-reaction law. For every action, there is an equal and opposite reaction. You can see this in collisions. Take, for example, an elastic collision. Elastic collisions are a very good example of this. Particle 1 collides with particle 2. In an elastic collision, both momentum and kinetic energy are conserved. So even if particle 1 stops, particle 2 will just zoom on. Inelastic collisions are when the momentum is conserved, but the kinetic energy is lost to internal energy. And thus particle 1 clashes into particle 2, and then they stick together, like this. And so, you'll get this type when you clap. Notice that they just stick together, my hands, and what's left is the internal energy that is released in the form of sound. So yes, that is Newton's laws. Those are Newton's 3 laws. If you like my lesson, please give a like, subscribe, and check out my other videos. If you want to see another topic, I'll be certain to read your comments and see your requests on other topics I can cover. I also do reaction videos, poetry, I do music. All that sort of stuff. So, thank you for watching. I am Professor Copperstein. Remember, there's always time for science. Transmission out.